for attending our tech talk today, and I'm sorry for the technical issues that we had. We are absolutely honored and very excited today to have Dr. Henry from University of Delaware to give us a talk on regression discontinuity designs for evaluation. However, before I introduce our speaker, let me go over some housekeeping issues. As you know, we are extending CME credits for our tech talks, and we will distribute the information via email to those that registered for today's event. If you did not register, you can still obtain CME code information from Lisa Maturo at ChristianaCare. Her email address is lisa.m.maturo@christianacare.org. Do not miss our June 26th ID series. That will be Dr. Martello from ChristianaCare, who will talk about Parkinson's disease, etiology, and subtypes. And finally, our next month's tech talk will be on July 9th, and that will be Dr. Yong Chen from University of Pennsylvania. We'll talk about using electronic health records in research. So also that will be very interesting for all of us. So again, I'm really delighted and honored to have Dr. Henry here to give us a talk. Dr. Henry has been Dean of the College of Education and Human Development at University of Delaware since 2019, as well as professor at the School of Education and Biden School of Public Policy and Administration. Prior to coming to University of Delaware, he was chair and professor of public policy and education at Vanderbilt University. He obtained a PhD from University of Wisconsin-Milwaukee. He has been extremely well funded. He has received over $29 million of sponsored research funding from the Institute of Education Sciences, the U.S. Department of Education, and numerous foundations and state agencies. He has multiple peer-reviewed publications as well as numerous books and book chapters. He has been a teacher, a mentor, has served on multiple dissertation committees. He has served also on multiple national committees related to education sciences, and is currently a principal member of the standing U.S. Department of Education panel on educational systems and broad reform. And finally, he has been invited nationally and all over the world to give keynote addresses at conferences as well as other prestigious presentations. So we are extremely honored and very excited to have Dr. Dean Henry here to give us this presentation. Thank you very much for coming.
Thank you so much for the introduction. I'm unable to see on my my screen what's going on. I'm getting a recording rather than the meeting. So I just think it's probably best for me to launch into the meeting and the substance of the talk and proceed. I can just give you the slides to use. Are you able to see me now?
Recording is on.
Yes. Yes, we can see you and we can see your slides.
I'm sharing the slides right now. I have the slides up.
We cannot hear you, unfortunately. Yes.
Can you hear me?
Yes.
Okay. I'm getting an echo, but I'll just proceed and just interrupt me if this is not working for you all. But first of all, I apologize for the technical difficulties today, and I will try to move through this directly and as quickly as possible to get through the main points of the lecture. I'd like to start by just kind of situating, if we can go to the first slide, regression discontinuity designs in what I have developed with a couple of colleagues for CDC as a rough hierarchy of designs for reducing bias and impact evaluation. I apologize again. I am getting an echo that I've just got to cut the, I believe I've just done that.
I just muted your computer.
The hierarchy of designs that we have on the screen is one that shows that regression discontinuity among possible designs for reducing bias and impact evaluation. Regression discontinuity is behind only randomized experiments in terms of producing causal estimate that's both valid causal effect estimates. Regression discontinuity requires one more assumption than a randomized experiment in order to estimate valid causal effects. And that one requirement is that the relationship between the forcing variable and the outcome variable of interest is modeled correctly. So I'm going to get into the basics and the rationale and the intuition behind regression discontinuity. And I just want to point out that the proof for this was done in 1972 by Arthur Goldberger at the University of Wisconsin. And I've got the mimeograph sheets on which the proof is written in Part A and Part B. If anybody wants them, I'm happy to pass those along. Let's go to the next slide. So the benefit of regression discontinuity is that it eliminates selection bias in the estimates of causal effects. So the way it does this is regression discontinuity breaks up any possible correlation between treatment and the disturbance term by removing selection bias from the estimate of the treatment effect. So in essence, by including a variable, a quantitative variable that's used to assign units to treatment, we're able to include that variable in the regression equation, which allows all the potential bias in selection to be removed from any correlation with assignment to treatment. So I'll show you the equation in just a minute, but we use in this, and what's very important to understand is that regression discontinuity, and this is often not intuitive for those of you who mainly do randomized experiments. Regression discontinuity assigns units to treatment on the basis of a quantitative forcing variable. And the quantitative forcing variable or quantitative assignment variable can be anything. Often in education, it's a measure of need or risk for negative outcomes if treatment is not, if the units don't participate in treatment. And my example today will be using an assignment to treatment for the lowest performing 5% of the schools in North Carolina. And we use the overall proficiency rate on end of course and end of grade tests in order to develop that quantitative assignment variable. So we have a quantitative assignment variable. Every unit in the proposed sample has a value on that. There's a cutoff on that, which was the 5% point for the example that I'm going to use today. So the lowest performing 5% of the schools in the state of North Carolina. Everybody below that cutoff receives access to treatment, and no one above receives access to treatment. So treatment is perfectly measured by the forcing variable or the quantitative assignment variable that we're using to assign units to treatment. So for this method to work, you have to have the quantitative assignment variable, and one of the first questions that's usually asked is, what does quantitative mean in this case? What's the strict definition? And by What Works Clearinghouse standards, currently, we believe that you have to have at least 4 units to the right of the cutoff and at least 4 units to the left of the cutoff that all contain 4 or 5 categories to the left, ordinal categories to the left, and ordinal categories to the right, in order that each contain units of the study sample for the assignment to be valid and the forcing variable to be considered quantitative. The common types of variables are often need or risk, but there have been a number of creative forcing variables that have been used, including several studies of the effects of pre-K using age for eligibility for pre-K at the state level in order to assign students to the treatment. There are 2 distinct types of regression discontinuity designs, sharp and fuzzy, and the assignment to sharp is if there's been strict compliance with assignment based on the forcing variable and the cutoff. Fuzzy is when there's been non-compliance, and that can be either units that were assigned to treatment not complying with that assignment, or treatments who have been assigned to the control group actually receiving treatment. And in today's example, we will go through the fuzzy results as well as the sharp. The sharp results are generally considered intent to treat estimates, and the fuzzy results compliance or complier adjusted assignment to treatment estimates, and we can get into that a little more deeply in the questions. I'm going to show you both and how we look at both of those today in the example. As I mentioned before, the single additional assumption that we need to consider the estimates that we will produce with a regression discontinuity design as valid causal effect estimates is that the correct relationship or specification between that assignment variable, and the example was proficiency in the case I'll use today, and the outcome variable, which are students' test scores and teacher turnover within these schools in the estimating equation. And today I'm going to try to take you through multiple tests of the validity of those relationships that have been developed over the years to help support the validity of the effect estimates through the RD design as causal. So go to the next slide. So the assumption is that the relationship between the assignment variable and outcome is smooth. We have a direct test for that. We're also going to directly test the validity of the assumption that no other changes occurred precisely at the cutoff, that the treatment did in fact occur, that there are no hidden treatments. There's a plausible mechanism linking the treatment to the outcomes, and this is an area where there's been lots of development, but the effects are robust or consistent closer to and further away from that cutoff that's used to assign units to treatment. So we're going to go through some fairly recent developments about doing an optimal bandwidth or an optimal sample size for you to estimate the causal effects through a regression discontinuity design. Next slide. So here's the basic equation that we're going to use to do the treatment effect estimates. And I'll go through why I is the unit level. And it does not necessarily require that the unit of outcome measurement is equal to the unit of assignment to treatment. In the example today, we're going to use student test scores as our outcome measure, and we're going to use assignment to treatment. The assignment unit is going to be schools. So we have the effect estimate here is delta 1, and Z is going to be our indicator variable for assignment to treatment. And in this case, this is the equation that we would use for sharp assignment or minor noncompliance in the assignment. And Z will be 1 if the assignment's to treatment and 0 if the assignment is to the control sample. I minus IC is the centered value of the forcing variable, and the F indicates, in this case, the function indicates a flexible functional form being used for the estimates in this case, but we're going to center the forcing variable at the cutoff, which will make our estimates of the effects local average treatment effects at the cutoff. So all of regression discontinuity effect estimates are considered formally local average treatment effects, and there are some ways that we'll show to look at the data to see if it appears to hold further away from the cutoff being used. The gamma Z I minus IC is the value that allows the slope of the relationship between the forcing variable and the outcome to differ on the treated group and the control group. And then our vector of covariance is represented by the G in this case with a idiosyncratic error at the end. So this is the basic equation we'll use as long as we're doing a sharp regression discontinuity design, and I'll show you the equations that we use when we need to do a two-stage least square instrumental variable estimates for fuzzy regression. So ready for the next slide? So just as a quick example, one of the most influential papers in this area is the effects of universal pre-K on cognitive development. The study was done in Tulsa, Oklahoma by Bill Gormley of Georgetown University and some of his colleagues there. And this is a brief description of the universal pre-K. It served 4-year-olds basically in the state public schools, and they were eligible based on age. So if we can go to the next slide. This shows the basic intuition graphically behind regression discontinuity designs. So you'll see that age, and then the dotted vertical line is the cutoff based on birthdays, so that younger children are to the left of that cutoff and older children are to the right. And so we've just graphed the relationship between age and test score values for these children. And you see that the left side, to the left of the cutoff, we have a representation of the control group of younger children in that darker solid line. Above that, to the right, we have the representation of the values on the test score for the children who participated in pre-K. And our counterfactual is the extension of the younger children's line into the older age group, assuming that without treatment, without access to pre-K in this case, they would have developed in a fashion, or the relationship between age and test score would have been consistent from the younger children through the older children, and the discontinuity at the cutoff, or the difference between those two, the dotted line and the light gray line, is the discontinuity or the effect of treatment. So in the absence of treatment, we would have expected the relationship between age and test score to look like the lighter gray line. After participating in treatment, the test scores actually look like the dashed line above that, and the difference between those is the discontinuity that we're using to estimate the effect of the pre-K on children who attended pre-K. So just one note, because you may be wondering, well, how did they do this, and why is this such an important factor? Pre-K in Oklahoma, as in every other state, is voluntary. So you can imagine that there would be considerable selection bias in the parents who would choose to enroll their children in pre-K. Perhaps the parent has assessed their child as being mature enough to go to an all-day or a half-day pre-K, and they enroll them, but other parents who don't believe that their child is developmentally ready for pre-K might resist, and that selection bias could be profound in terms of an uncontrolled design. But in this case, we expect parents to select using the same type of criteria overall from year to year about enrolling their children in pre-K, and this design allows us to control for that potential selection bias because we measure the test scores at the same period. For the pre-K kids, it's in the fall when they enter kindergarten, so it's after they participated in pre-K. And for the younger children, their test scores are measured at entry to pre-K, and so those children have elected to, their parents have elected to enroll them in pre-K, and therefore the selection bias, if it's consistent from one year to the next, could give us an unbiased estimate of the treatment effects. If we can go to the next slide. This just presents the findings from the abstract of this paper that was published in 2005. This research design has gone on to be replicated in multiple states over time. And you see that there are large positive effects, standardized effect sizes of 0.79, for the impact on letter word identification of 0.64 on the spelling score, and of 0.38 for the applied problems on the Woodcock-Johnson achievement tests that were being used. And there was positive effects heterogeneously for each of the racial ethnic subgroups, as well as for children whose families were eligible for receiving free or reduced price lunch. So this study led to a great deal of confidence that universal pre-K has succeeded in enhancing school readiness of children for whom it's provided. This is a very controversial study now for reasons that we don't necessarily need to get into today. And these findings have not been replicated in some of the subsequent analyses. And again, we could talk about that, or I could refer you to a couple of papers that have reviewed this literature and done meta-analyses, including these studies. If we can go to the next slide. So the basics for the regression discontinuity design implementation is assignment to treatment is based on a forcing variable, and that's sometimes called a running variable, or as I've said, an assignment variable, quantitative assignment variable. And I want to note, this assignment variable doesn't need to be a perfect measure of the construct that it is being based on. So for our purposes today, proficiency on student test scores is not a perfect measure of student achievement. It takes 1 point in the distribution of those test scores, sets it at a cutoff, and so it's not a perfect measure, but as long as it's used to perfectly assign to treatment, it does not have to be a perfect measure of the variable that you're using to risk or need or whatever that variable might be. It just has to be used as a perfect assignment to treatment, not a perfect measure of the concept it's intended to represent. The focus for our analysis is going to be observations around the cutoff. We're going to eliminate selection bias by including the forcing variable in the estimation equation, and that by inclusion of the forcing variable in the proper form with the proper specification of the forcing variable will eliminate any possible correlation between the assignment to treatment, the Z in our earlier equation, and the disturbance term, and therefore the treatment effect is unbiased. As I said before, it's a local average treatment effect. If it's a sharp design, and it can be a compliance adjusted or intent to treat treatment effect, and we'll go into those estimators in just a minute. So next page, please. So here is the equation that we're going to use today. It's a version of the equation that you saw earlier, and GLP is the variable. It stands for grade level proficiency, and we're using that variable to assign schools to the school reform or school turnaround treatment. And if it's below the cutoff, then they're assigned to treatment. So beta 1 in this case would be the coefficient of interest in the equation, and the beta 2 will be the coefficient on the forcing variable itself, and beta 3 will or the term included in that will allow the slope to vary on each side of the cutoff. Just make a note about covariates here. Covariates are unnecessary for an unbiased treatment effect as long as selection bias is the only bias that you're really focused on at this point. They can be added for efficiency purposes, and we'll go through some of the considerations when we're doing this as we go through the example. But I'll move through the example, and then I'll start with the validity checks, but I will stop here for just a moment, and please let me know if there's a question that I need to address at this point. Okay, let's move on to the next slide. So this is a term that we'll use throughout the rest of the lecture today, and it's called bandwidth. And bandwidth simply is the range of the forcing variable that you use to estimate the treatment effects. So if you'll move forward. So we've drawn this bar. It should be exactly over the zero. It appears to be a little off, but it should be exactly over the zero, representing the cutoff. And we've centered our forcing variable at the cutoff. Advance, please. So a bandwidth, this would be a bandwidth of about 7 units on each side of the cutoff. Advance it. And this would be a narrower bandwidth. Obviously, a trade-off between bandwidth and so the narrow will give us the narrow bandwidth will give us a range of the analytic sample that we're most confident will get an unbiased causal effect, but it also reduces sample size and therefore the statistical power to detect an effect when it in fact occurs, and therefore we are going to be concerned with the bandwidth as we move throughout and begin to estimate our effects. Advance, please. The second term that we're going to need to be familiar with is a kernel, and the kernel is a function that assigns weight to these particular observations. So the bandwidth itself, you start out with what we would call a rectangular kernel, which is equal weighting to each unit in the bandwidth. So advance. And so this is the graph moved down here for the rectangular or uniform weighting, and advance. Oh, this moved right to triangular. I apologize. This is automated in the slides. So what should have appeared first is a rectangle over this space that looks a lot like the one above. And then the triangular weighting that we're seeing the graphical illustration for now indicates that the units closest to the cutoff are weighted more than the units far away from the cutoff. So it's a triangular weighting, and the Gaussian is simply a weighting that follows the Gaussian distribution, and so we can advance the slide. Those are 3 options that you have in Stata. And advance again. So 2 graphs you will always see in regression discontinuity papers. The first graph is assignment to treatment, and you see that the vertical line, once again, is at the cutoff, and on the left we have bins of the sample that were not assigned to treatment, so those are the untreated units, that's a 0, and then you see to the right of the vertical line bins with the units that were assigned to treatment, and there's no crossover, which would be represented if you advance. So this is sharp and advance. This is fuzzy, so you see 2 units to the right of the cutoff at the 0 point now. Those are non-compliers, and you see 3 units to the left of the cutoff at the value of 1, and those are non-compliers to assignment to treatment. So that represents a fuzzy design, and these graphs are these days nearly always included in a regression discontinuity paper. Advance. You'll also always see a graphical display of the estimated treatment effects. And so this uses the correct specification for the forcing variable on both sides of the equation and the distance if you advance. between these two represents the discontinuity. That discontinuity is the treatment effect at the cutoff, and that will be the treatment effect estimate that we yield in the estimation equations that we've looked at before. Advance. So the North Carolina transformation, I'm going to go really quickly through this, assuming that very few of you are interested in the mechanics of school turnaround, and so we can get to the empirical work, but I just want you to know just a bit about what we're looking at today. So this was a 5-year, $5 million IES grant that we're finishing up the 5th year of now. Advance. So the School Turnaround Initiative identified 75 schools in North Carolina. The assignment to treatments based on the 14-15 performance composite, and that's the same thing as the grade level proficiency, or the GLP. They received services in 2015-16 and 2016-17, and we're going to, because the services were slightly different in both those years, for today's purposes, we're going to look at the effects in each of those years separately. Advance. So the performance composite varied based on the level of the schooling, elementary, middle, and high, and we appropriately center by subtracting the cutoff from the actual score used for schools at each of those levels. So we have a cutoff that's aligned at 0 for each of the 3 levels. Advance. So this tells us, just sets the eligibility criteria, so that out of the 2,300 schools in North Carolina in that year, 331 were eligible, and that's the full study sample for this study. We're going to use that in some cases as the analytic sample, but we're going to set bandwidth specifications. Advance. So the district and school transformation team that was implementing this transformation requested participation, but they didn't get complete cooperation. So there's a small amount of non-compliance on both sides of the cutoff. Advance. So we see here the specific graph for this example that shows that to the left of the cutoff, so those lowest scoring schools were all given access to treatment, but where you see that deviation, if you advance on the left, those are the non-compliers. And then on the right, you also see a small amount of non-compliance that control schools actually received the treatment. And this is primarily due to requests from districts that one of their schools or another one of their schools be included in addition to the one that was going to receive treatment on the left side. So we consider this fuzzy. I will say that one of the things that is not yet well worked out in regression discontinuity design is what designs are fuzzy and what designs are sharp, and how much non-compliance is needed for you to do a fuzzy design. In general, I recommend doing both analyses and looking for consistency between them, but we'll go through both to the extent that we have time today. Advance. So this just lays out the difference and the difference in approaches. The sharp design is if compliance is 100%, it will be a late design, and if it is not 100%, it will be an intent to treat. So in our case, we would do the estimation as if it was sharp, but label the effect estimates as intent to treat. And we're also going to do a fuzzy, which is a local average treatment effect for compliers, and that's rescaling using the two-stage least squares, instrumental variable approach that probably everyone is familiar with. Advance, please. So for our estimates, I've shown you today two of the bandwidths, and I've got the references later, bandwidth calculations. If you are working with nested data, as is the case here, because students are nested within schools, the CCT band provides an adjustment for nested data, and the IK bandwidth, if you're not using nested data, the IK is usually the best bandwidth. In our case, the IK is really not usable, but I just put it here to show you your options in terms of CCT. And again, I'll give you the names and the reference in just a minute. The IK, and then no bandwidth with a triangular kernel. In most of the work I do in education, it's common to prefer the triangular kernel, but that may be specific. You see in this case that the results for 2016 are only significant in one of the bandwidths, so we wouldn't view that as consistent. But in 2017, we had negative and significant effects in all three of our bandwidths. And What-Works Clearinghouse standards for educational research requires that you have consistency in three bandwidths for a valid effect estimate. And you see that this is actually a negative effect of 13% of a standard deviation unit. So this was a program that actually did harm and had negative effects on student achievement. And I can, if we have time, try to get into a little bit of substantive explanation for this. But if we go to the, I'll go a little bit more into the first stage Z if we have time today, but that's just a way of establishing that our first stage equation is, we have a strong instrument in this case. We can advance. Oh, here we have the results for the SHARP analysis. So this is the intent to treat. And you see, once again, we have very consistent estimates in 2017, inconsistent estimates of the effects in 2016. So in the second year of the intervention, we saw negative and significant effects on the test scores of these students through both SHARP and fuzzy design. We can move forward. This shows graphically, as I indicated we would need to do, and in 2017, you can see a clear discontinuity at the cutoff, and this just gives some specification about this particular design and the bins on both sides. If you could advance, please. These are our results for teacher turnover, and we see that in that second year, again, we have reasonably consistent positive effects, which means teacher turnover actually increased in that year. We tried to test this as a mediator of the negative effects on students, and it is not the mediator, it's another effect. So we increased teacher turnover, and in the paper that I've provided, we show that that teacher turnover is not necessarily strategic in that they're not losing more of the less effective teachers in the second year of the reform. If we can advance. So here's the SHARP RD results, and you see that we have significant positive effects that show that teacher turnover was increased in the second year. These are our intent to treat estimates again because they're sharp. But they're fairly consistent in size and definitely consistent in direction with the fuzzy treatment effect estimates. Advance, please. Here are the teacher turnover results, which looks like the teacher turnover was qualitatively but not statistically significantly lower in 2016, and the discontinuity there is obvious at the cutoff for 2017. Advance, please. So this is a good point to stop and do a check. As you noticed, I had 75 slides in the presentation today with no real hope of getting through 75, but I wanted them for your reference in case you're interested in implementing the What Works Clearinghouse standards or some version of those. But we're at 12:58, and this is the part where the validity checks get interesting, but if there's a question about one or more of these, I'd be happy to answer, but I think for the sake of time, we probably don't have the option of going through these checks today. So I hope what I've done so far gives you a little bit about the intuition and the implementation and estimation of these effects, and maybe I can rejoin you another day if you're interested in all the validity checks. But let me stop for a question if you have one.
Well, thank you very much, Dr. Henry. This was great and very informative.
Okay.
I'm sorry, go ahead.
I am not hearing any, so is there a suggestion from Lisa or Claudine about how we should proceed now?
Yeah, can you hear me? Can you hear me?
I can't. I'm not hearing you.
Oh, well, that's a problem. I am unmuted. Lisa, did you unmute everyone? Could you unmute?
Let me.
You hear me?
Yes, I can hear you.
I can hear now, yes.
Oh, okay, great. No, I was just saying that this was extremely informative. Thank you so much. And I think it's very relevant to our work in the Value Institute, because we do a lot of observational study trying to evaluate treatments or interventions. And one of our major issues is really selection bias. So I think this is really great, and it kind of starts the conversation, and I'm sure we will have more example. And if you don't mind, if we can go back to you and ask you questions when we start doing some analysis to try to figure out our selection bias issues. What we've done until now was using propensity score matching or instrumental variables. I don't think we've used a regression discontinuity, unless any of the statisticians, Zugwe or Keshab or Rick, have had used it before. I don't think we have. But I mean, for us, it's really a great technique to learn, and I mean that's really wonderful.
Great. Well, thank you for having me. I really appreciate. As you might imagine, I don't get a chance very often in my role as the dean to talk about the technical side of the work that I love so much. So I really appreciate being invited, and I'd be happy to join in a conference call if that's useful at some point and talk about different ways of seeing if a forcing variable is possible to use. Because it's often a measure of need or risk, I found that practitioners are a lot more comfortable using one of those types of measures rather than random assignment. And if we can get strong causal effects but let them assign based on need, it can be a very useful strategy.
No, exactly. And that's what we face all the time in our analysis, because we do a lot of work on electronic health records, which are really made for care, not so much for research. And then we try to, to have inferences, from analysis of these electronic health records. And selection bias is really always something that we face and that we try to resolve. So it is really great. I learned a lot, so thank you so much. I'm sure that everyone else on the phone did. But we will get back to you because I'm sure we'll have plenty of questions. Thank you so much.
Okay. Thank you so much. Bye-bye.
Bye.